Hello everyone, I'm Longshu from CSCI2021 and I'm glad to introduce you interactive in-demo transactive learning for microscopy image analysis. When deep learning is applied to medical image processing, we found that training data and test data are often from different patients. And we assume that the potential high patient's level difference may limit the generalization of the trained model, which causes bad performance on test data. Inspired by transactive learning, which makes use of information of test data in the training phase, we just embedding the test data into the process of training, which helps model learning the potential difference directly. And although we combined iterative in-demo method to further optimize the performance of the model. This image shows the overflow of our iterative transactive in-demo learning method. And I'll introduce step by step. Step 1. We use all the training data to get initial in-demo model. And in the experiment setting, we just use train 3 model and they have same architecture. Step 2. We average those predictions of 3 models to get the in-demo result. And here we call the predicted label of test data as pseudo-label. The averaged probability as confidence score. Step 3. We based on the assumption that samples with higher confidence scores are more likely to be correct. So we choose high confidence samples. We have a threshold T, and if the confidence score is larger than the threshold, we just keep that sample. Step 4. We then retrain 3 model with all the trained data and randomly selected test data with pseudo-label. And last is the step 5. We iterate step 2, 3, and 4 until the prediction becomes stable. So let's move to the experiment part. We use 2 medical datasets to confirm the performance of our method. One is white blood cancer microscopic images, and another is breast histopathology images. And here we just use the subset of it because the whole dataset is too large. For both the 2 datasets, the training data and the test data are from different patients, which means the potential patient's level difference exists in those 2 datasets. Then let's move to the experimental analysis. Here we compare our method with traditional in-demo methods on 2 datasets to show the novelty of our method. This table is the result of blood cancer dataset. SE is short for simple in-demo, which we average 3 models trained with all training data. And EB is short for ensemble, also means bagging. We average 3 models by randomly selected 80% data. And as mentioned before, our result is from averaging 3 models trained with all data and high confidence test data. We can see clearly from this table, our method performs better on the different model backbones. And this table has the same settings as previous ones, but the result is from the breast dataset. And the data in the right boxes show that in different datasets, our method just also keeps similar outstanding performance. We then did some simple evaluation study to show the effectiveness of each component in the proposed iterative transactive learning method. This table shows the results of the general model and transactive learning model with different backbones. We can see that the third row, which is transactive single model, we just use one model which trained with all data and high confidence test data. The result performs better than the second row, the general ensemble model, which means the transactive part is important for the whole process. And the first row, which is our method, has the best performance, shows that the ensemble can further improve the performance. And here those two images shows the effectiveness of iterative training. We can see from the left image that the performance is becoming better as the iterate number increases. And for all the backbones, the performance saturates after a few iterations. And similar findings are observed also with the breast dataset in the right images. We can see the accuracy is becoming higher as the iteration number increases. Then we explore the accuracy of different combinations of parameter T and parameter S. Our method has two experimental parameters: the threshold T to determine the high confidence predictions, and the percentage S to determine the number of test data to be selected. From this matrix, we can see that when threshold equal to 1.9 and the percentage equal to 1.8, we can get the best performance. At last, let's do a quick conclusion. First, we propose an iterative ensemble transactive learning framework. And second, this method can make good use of information from test data. And third, it is helpful for the dataset that exists large patient-level difference. And fourth, from those experiments, we can see that all methods can keep performance under different datasets and different model architectures. That's all. Thanks for your listening.